Okay, so we're going to start with by looking at our own decimal or base 10 system. This is the system you would have learned since primary school. And it's called base 10 because, well, it's based on 10 individual digits, 0 to 9. And they're the fundamental building blocks of our number system, the decimal number system. And you should remember that we build our system based on powers of 10. So the first power is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, and so on. Now if that doesn't look familiar, 10 to the 0, well, anything to the power of 0 is simply 1. 10 to the 1 is just 10. Then you've got 100, 1000, and so on. And what you can see is this is the system that we learned to teach our own system. It is ones, tens, hundreds, thousands, and so on. So just to refresh your memory, if we take a number like 5036, that's broken down with 5 by 1000, no hundreds, 3 tens, and 6 units. And just to really expand the point, if you were to do the maths on that, that's 5 by 1000, 3 by 10, and 1 by 6. And when you get the answers to each of those, you simply add them up and you're back to where you started, 5036. So there exists many other number systems not based on 10, and that's what we're going to look at now. So some of these other systems, some are more complex and some are more simple than our own existing system. So computers rely on a binary system. A binary or base 2 system has only two fundamental components, 0 and 1, as opposed to our decimal system that has 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So using just 0 and 1, we can calculate numbers. And just like the decimal system, it's based on powers, but powers of 2 this time. So we're going to start off with 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. So expanding out these powers, we get 1, 2, 4, 8, 16, 32, 64, 128, and so on to infinity. Binary is best demonstrated using an example. So let's take a binary number 1101 and let's see what it means in decimal. So if we line it up against its guide 1101, that means 1 by 8 and 1 by 4, no 2s and 1 1. And if we simply add each of those up, we end up getting 13. So 1 8, 1 4 and 1 1 give you 13. And that is what the equivalent is in decimal. So 13 decimal is equal to 1101 in binary. Looking at a second example, 101010. So again, we line it up under each component, 0 1 0 1 0 1, and we simply add together their values. 132, we've got no 16s, but we have an 8, we have no 4s, and we have a 2. So it's 32 plus 8 plus 2, and that gives you an answer of 42. So 42 in decimal can be represented as 101010 in binary. A simple example to finish off. Taking the binary number 1000, when we line it up under the values, we get 1 8, no 4s, no 2s, no 1s, which when you add it all together gives you the value of 8 as a decimal. The hexadecimal system uses 16 basic components, as opposed to decimals 10 or binaries 2. The 16 components I've listed out in black. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E and F, where each of these represents a single number, and I've listed in blue the value of each. You can see that A is worth 10, B 11, C 12, D 13 and so on. So I've also written out the powers of 16, just like we wrote out the powers of 10 for decimal and the powers of 2 for binary. It's 16 to the 0, 16 to the 1, 16 to the 2 and so on. Filling in their values, 16 to the power of 0 is 1, 16 to the power of 1 is simply 16, to the power of 2 is 256, to the power of 3 is 4096, to the power of 4 is 65,536, and 16 to the power of 5 gives you 1,048,576, and so on. You can keep continuing to build the powers. Again, we'll use an example to demonstrate. So if we take a hexadecimal number 2F3, for example, well, we line up the 2, the F and the 3 on the right hand side of our little guide, so 2F3, and we repeat the steps of the previous examples. That's 2 by 256, that's F by 16, and that's 3 by 1. Now I know that F looks ominous, but if we look at our guide above in the black and the blue, you can see that F is actually worth 15. So we can replace that F with 15. Now we simply calculate the final value. 2 by 256 gives you 512. 15 by 16 gives you 240. And 3 by 1 gives you 3. Summing them together, you get 755 decimal. So 755 in our number system, decimal, is the equivalent of 2F3 in hexadecimal. And you can start to see the efficiency of the hexadecimal system here. So let's give it a go with some conversions. So this is what you're likely to be asked in an exam. So we'll take the first type, which is to convert a decimal number, or base 10, into binary, which is base 2. So I've got 3 examples written down here, and we'll start off by converting 32 to binary. So you can see the binary guide I've written above. It goes from 1, 2, 4, 8, 16, 32, 64, 128. If we start looking from the left hand side at the 128, we know that there's no 128 in 32. So 128 will not be one of our building blocks. Neither will 64, it's too big. So what we're looking for is a number greater than or equal to what we're looking for. Now here comes 32, so we know 32 is definitely part of the building block. In fact, it's the entire thing that we're looking for. So there is no requirement to have anything else. There's no need for 16s or 8s or 4s or 2s or 0s. So what we end up with is 132 and none of the rest, so 0, 0, 0, 0, 0. And that's your final answer. Now you could put on a leading 0 like that, but that's the equivalent of saying 032, so there's no real need for a leading 0. So we don't really put the zeros that appear on the left. So our final answer is 1, 0, 0, 0, 0, 0. Moving on to the second example, which is 55. Again, we'll start on the left and dismiss anything that's too big to be counted. So 128 is discounted, 64 is discounted, but we do need a 32. Now 32 away from 55 leaves you 23, so we're still needing 23 to add up to 55. So we look at the next number, which is 16, and it's smaller than 23, so we take the 16. And now with a 16 and a 32, that leaves us at 48, so we're just 7 shy. 8 is too big, so we can't take 8, but we can take a 4, which leaves us 3 short. We'll take the 2, which leaves us 1 short, and we'll take the 1, which finishes us off at 55. So writing down our final answer, we end up with 110, 111. In our third example, we've got 190. So again, the next number off to the left that we haven't written down is 256, which is too big. But we do know that we will need 128. So let's mark that in. By using 128, that leaves us needing 62. Okay, so looking at the next number, 64 is too big, so we can't use it. But we can use 32. So 32 away from 62 leaves us needing just 30. 16, we can use that. If we take it away from 30, we're left with 14. So we'll take the 8, which will leave us needing 6. We'll take the 4, which needs to be fixed. So we'll take the 4 and we'll take the 2. And that leaves us at our total of 190, so we can leave 0 and under the 1. Writing down our final answer, that gives us 101, 111, 10. We should double check our answer by ticking off and counting. 128 plus 32 is 160, plus 16 is 176, plus the 8 is 184, plus the 4 is 188, plus the 2 is 190. And that matches the answer we were looking for. The next set of conversions are going in the opposite direction. We're going to convert binary to decimal. So, taking the first example of 111, we simply align it up under the binary guide from the right, 111, and we add together the numbers. So we've got 14, 12 and 11, which gives us 7. So it's as simple as that. 111 is 7 in decimal. Looking at the second example, 110101, again we line it up. So 101011, reading from right to left, and again we just add up their totals. 32, a 16, a 4 and a 1, giving us a total of 53. The last example follows the same lead. From right to left, 010011, and again it's 32 plus 16 plus 2, and we total them up to 50. So the next conversions are going to be between hexadecimal and decimal. Now you're really starting to get into the weeds here. Converting hexadecimal to decimal is a little bit easier than converting decimal to hexadecimal, but we'll see that later on. So in addition to having the guides at the top of the page, beside the hexadecimal guide, I've written out its numbers or its digits or components, whatever way you want to think about them, 0 to 9 and A, B, C, D, E, F. And underneath them, I've written in their values all the way from 0 up to 15. So they're going to be essential tools when we go to convert. So the first hexadecimal number we're going to look at is the number 23 or 23. Just like the previous conversions, we write it in 2 and 3 on the top of the guide, and that's 2 16s and 3 1s. So we add our two answers. So 2 by 16 plus 3 by 1. 2 by 16 is 32, plus 3 is 35. So that is a decimal number. So in other words, 35 in our usual number system can be written as 23 in a hexadecimal system. The next example looks a little strange, AF. So again, we place it in AF. So just like the previous example, that means A by 16 plus F by 1. Now of course we just look at our conversion chart up above in the blue and the green, and we can see that A is actually worth 10. So you simply substitute that in. So that's actually 10 by 16. Plus F is worth 15 on our chart. So that's going to be 15 by 1. So it's 160 plus 15 is 175. Starting our third example, 8BE, we follow the same rules. So again, that's 8 by 256 plus B by 16 plus 3 by 1. And the only substitution we have to do here is we have to replace B with its equivalent, which is 11. And we simply go ahead and calculate out the result. The final total is 2,227 in decimal. Converting from decimal to hexadecimal can be tricky. I'm going to go through these three examples in a straightforward manner, but I'll follow it up with examples of how I use the calculator when doing these types of calculations. So there's our hexadecimal list, and let's start with the number 12 decimal and converting it to hexadecimal. Well, this one is quite easy. We know that hexadecimal goes all the way up to 15 with a single symbol. And if we look at that list and highlight it, you can see that the number 12 is represented by the letter C. So therefore, that's a straight conversion. 12 decimal is simply C in hexadecimal. For our next example, we're going to examine the different powers. So moving from, again, left to right on the hexadecimal list, obviously 65,536 is not going to be a building block of 18. So we can ignore that safely. We can also ignore the 4,096 and the 256. However, there is a 16 in 18. How many 16s are in 18? Just the one. So we need one 16. That leaves us needing 2, which simply falls to the units. So we can write 18 in decimal as the number 12 in hexadecimal. Things are about to get tricky in this example. We take the 8,562 and we can rule out the 65,536 because it's not a building block. But what about the 4,096? Well, our first thing that we need to know is there are two 4,096s within 8,562. So we write down 2 of those. Now we need to figure out what's left. So we need to multiply 2 by 4,096 and take our answer away from 8,562. And we find out that we have a remainder of 370. And we move on to our next number. How many 256s are in 370? Well, the answer to that is 1. Taking the 256 away from 370, we end up with a remainder of 114. 114 is now our new target, and we move on to the next number in the hexadecimal list, which is 16. We now need to figure out how many 16s are in 114. And the answer to that is 7. 7 16s give 112. That leaves us a remainder of 2 to be found. So that's going to simply be made up by 2 units. And so our final answer is 2172. So that represents the number 8562, but in hexadecimal. So now I'm going to do a conversion with a long form answer. So what I'm going to do here is I'm going to step you through what I'll be putting into my calculator as I go through this challenge. The number we're going to convert is decimal 36,522. You see it on the left there. On top you can see the different powers of 16 going from right to left. So you've got 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, and I've stopped at 16 to the power of 4. I know that 65,536 is beyond the scope of this question because it's bigger than my original number, so there's no way it's going to be involved in my building block, and I can rule it out now. On the right hand side of the screen, you're going to see exactly what it is I type into my calculator here beside me to guide you through my own moves in solving the question. So we'll start with 16 to the power of 3, or 4,096. The first question we have to solve is how many 4,096s can we fit into 36,522. So to do that, we turn to our calculator and I type in 36522 divided by 4096, and when I get my answer it looks like this: 8.91650390. Now, the only part of that I'm really interested in is the 8, because that means that 4096 goes into 36,522 8 times with some remainder which I'm not sure about. So this decimal places after the decimal point, they are irrelevant right now except they tell us there is a remainder. So I'm going to go ahead and put my 8 in there. Now, when I take away those 8 4096s from my original number, I need to know what the remainder is. So to do that, I need to know what 8 multiplied by 4096 is. So again, I go to my calculator, 8 multiplied by 4096, and I get 32768. To get the remainder, I need to know the difference between that number and the original number. So again to the calculator, and it's 36,522 minus 32,768, and for that I get 3,754 remainder. That means when I get my 8 times 4096 and take it away from my original number, I have a remainder of 3,754, which I now need to deal with. The next number along is 256, which is 16 squared, and so I repeat the process. I need to know how many 256s is in 3,754. I go to my calculator, and it's 3,754 divided by 256. And for that we get an answer of 14.6640625. Again, I'm just going to repeat myself. That means that the 14 is the important one. There's 14 256s in the number 3,754. And again, I need to know what the remainder is exactly. So I say, what's 14 256s? And that is 3,584. And now I need to know the difference. So I start it with 3,754, and I'm going to take away 3,584, which means that I end up with a remainder of 170. Now, 170 is my new target, and I move on to the next number, which is 16 to the power of 1, or simply 16. And I repeat the process. How many 16s are in 170? So the answer comes out to be 10.625. Once again, the 10 is the important part. There's 10 16s in 170, so I fill in my 10 and I calculate my remainder. Now, there's really no use for the calculator at this point because I've put in 10 16s, which is 160, so I should be able to work out that the remainder is 10 from 160 to 170. But again, if you're not confident, you can use your calculator. Now, there's nowhere else to go because all that's left are the units, so that remainder 10 simply goes into the unit category. So we're nearly done. We've now got 4 answers, and technically these are 4 separate digits in our hexadecimal answer, but of course we can't have a digit having 2 digits within it, so we need to make sure that these are fully converted to hexadecimal. And if you look at the little table I've drawn at the bottom of the page there, you can see that 8 in decimal is the same as 8 in hexadecimal, so the 8 stays. The 14 needs to be converted to the letter E per the table, and the 2 10s, well, each 10 can be converted to the letter A. So our final answer is 8EAA, and that is a hexadecimal version of the decimal number 36,522. And at this point, we've completed the question.